Hello, atmospheric science students. Dr. Shragi here, and I want to show you a little bit about this Excel spreadsheet that I've posted for you on Blue Line. It's called Numerical Integration Examples for ATS 570, and I just want to use it to show you a little bit about how we can use Excel to solve approximations for integrals in endpoint rules, midpoint rules, trapezoid rules, and Monte Carlo simulations, or Monte Carlo integration rather. All of them I'm going to be using the same integral. It's this integral from 0 to 10 of 12 plus x plus the sine of 20x dx. The right answer, if you actually evaluate the integral and plug in the endpoints and so on, is 70.02 something or other. And what I want to do is show you that we get slightly different approximations for each of these methods. I'd really like to show you like graphs of this where, you like what we drew in the pencast, where you could see the curve of the integral and then the different little rectangles that are being used to approximate the area under the curve. But surprisingly, Excel is terrible about that. Excel is actually not very good at putting, making that kind of bar graph or whatever you would want to call it. Excel doesn't have that functionality built in to put that on the same curve as a line curve and then have the bars touching each other and so on. There doesn't seem to be any way in Excel to do that, so we aren't going to be able to visualize what we're doing. We're just seeing how it's actually done. So in this first example here, I'm going to do an endpoint rule approximation where n is equal to 10. So up here I made myself a little table. A and B, the endpoints of the integral, are 0 and 10, and the number of rectangles I'm going to be using for my approximation is 10. If you remember, delta x is, the equation is b minus a divided by n. So here's my equation. Again, you can see it up here in the equation bar. That's b minus a divided by 10. And then I built a table down here where I have 10 rows, one for each of the 10 rectangles, labeled from I equals 0 to I equals 9. And the first thing I need to know is the value of x that I'm going to be using. Now, this is the endpoint rule, so this is the value of, let me put a little x right there just so you see what I'm talking about. The value of x that we're going to be using for f of x is then, the x is a plus I times delta x. So I made my little equation here of a times I plus delta x. I didn't really notice on here, I did it using absolute references where there are the dollar signs in the addresses. If you don't know how to use absolute references, a perfectly reasonable way to do this would be to have defined these ranges, called this one A, called this one B, called this one delta x, and then just make this a plus I times, well, I would be one cell over to the left, times delta x. That would work as well. Then I made f of x, where, so here's my function here. It's 2 plus the cell to my left times 20 times the cell to my left. Okay, so this is just a little table here. And then I made another column that is f of x times delta x, because that's part of the integration. Remember, the approximation that we're going to be using here then is the sum of f of x times delta x for all values of I from 0 to n minus 1. So here are all those values of f of x times delta x that are in my endpoint rule. And then I made a sum. The function for sum is just equals sum. And then I selected the range from, well, we actually do that one by hand here. Equals sum of, and then I chose this range. All right. And I get 65.8. That is an approximation to the true value, which is 70. And I'm not going to say that that's all that great of an approximation, but we'll see that there are other examples of endpoint rules with bigger values of n that give us better approximations. So like here on the second tab, I have said evaluate the following using an endpoint rule with n equals 100. So we have 10 times more slides, more slices here, more rectangles. And again, this true value of the integral is shown here. All right, so here I put in the same values of a and b and my value of n, which is 100 now. That makes my delta x only 1/10. All right. Now I took a whole lot longer, all these values of I here, all the way down to I equals 99. So we have to go from I equals 0 to I equals 99. But actually, these functions are all just the same as what they were before. Here's x, right? It's a plus I times delta x. Then here's f of a plus I times delta x. We're going to call that f of x. And then here's f of x plus delta x. I'm sorry, f of x times delta x. And I just copied these all the way down to row for the value of I equals 99. Okay. All right, now I can just come up with the approximation to that integral because it's the sum over all these values of f of x times delta x. All right, so I just did the same thing here, equals sum. Here, I'll do it again. Equals sum of f of x times delta x. Now, before I use my mouse to select, I could do that again here. Let me just do it for you. F of x, we're going to sum up from all the way down to the bottom column there, and we get 69.56, which is getting to be a better approximation to the real answer. Okay. Let's actually do the same thing again for n equals 1,000 on the next tab here. Here's my endpoint rule for n equals 1,000. All right, so the same sort of thing here. A, B, n equals 1,000, delta x. All right, and made that same table I had before. All right, except now it goes all the way down to 1,000. It goes all the way down to n equals 999. All right, I'm going to go back up to the top here. So we have all those same equations here. Now we're going to be summing over 1,000 values of f of x times delta x. I'm going to show you a little shortcut here that works at least on a PC. I'm not sure if the same shortcut works on a Mac. But equals sum of, okay, if I position my cursor on the first cell and hold down the shift key, okay, position yourself on the first cell, hold down the shift key. This is a good trick in general. If you hold down the shift key and use the arrow keys, you're just selecting an area. Okay? If you hold down the shift key and hit end down, it'll take you to the last row. So hold down the shift key, then tap end and tap down. It'll take you to the bottom of it. That works great when you're talking like literally hundreds of cells. Anyway, our value of that sum across all of that is 69.9799, which is getting to be an awfully good approximation to the number 70.02. So, okay. But that's an awfully big value of n. N equals 1,000. Okay, endpoint rules are easy to visualize what's going on, but they are they're not so great. They don't approve. It takes a very large value of n before you get a very accurate approximation to the true value of the integral. We can switch on the next tab to a midpoint rule. Now we're going to use a midpoint rule with n equals 10. Same sort of thing here. We're going to have a, b, n equals 10, makes my delta x equal to that. Okay, so here's my 10 rows. It's from I equals 0 to I equals 9. Here's the value of x that we're going to be using. Let me put x right there just so you understand. X is in the midpoint rule equal to a plus the quantity I plus half times delta x. So here are my values of x. All right, then that makes this f of x. All right, just plugged in my equation, 2 plus the cell to the left plus sine of 20 times the cell to the left. And then that times delta x in my last column, and then our sum is just the sum of all of these f of x times delta x's, as is then given in the equation for the midpoint rule. And we get, with a sample of n equals 10, we get a value of the approximation to the integral of 69.53 basically, which is not a terrible approximation to 70.02. 70.03, I guess, if you round. But notice we can get it a whole lot better if we go on the next tab to n equals 100. If we use the midpoint rule for n equals 100, all right, you can see we did the same sort of thing again. We just did it all the way down to the bottom for 99, and I equals 99, so we have 100 cells. And we sum them up, and we get a sum is equal to 70.03, which is getting to be really close. I mean, we're within 0.01 of the right answer. And in fact, our midpoint rule, if we got all the way up here to n equals 1,000 on the next tab, look what we get over here. We get the sum is equal to 70.026. It's not until like our fifth digit after the decimal point that we're off at all. This is an awfully good approximation to the right value of the integral. Sure, it took as large sample size, n equals 1,000, but boy, that's an awfully good approximation to the correct integral. But it gets even better if we use a trapezoid rule. Okay, now again, I really wish I could do this in Excel, but Excel just does not visualize this stuff very well. It does not have a built-in chart type that makes this stuff work. All right, but trapezoid rule integration. Okay, so here's our cells, our values for n equals 10. All right, now for trapezoid rule, you have to know x on the left side of the trapezoid. So here's x, I'll call this x on the left side. And you have to know x on the right side, which is, again, these are given to you in the equations for the trapezoid rule. But on the left side, it's a plus I times delta x. And on the right side, it's a plus the quantity I plus 1 times delta x. And then for each of those, you need f of that. And then there's an equation for the area of the trapezoid that is delta x wide, and then the average of the bases tall. And so here are your 10 trapezoids areas, which you just add up to get your approximation to the integral. And check this out. I mean, with only n equals 10 little trapezoids, we're actually not a terrible approximation. Here's our approximation to the integral, and there's the real value. We're already not terrible with only n equals 10. And in fact, if we went and looked for n equals 100 little trapezoids, check out, we're already up to 2 decimal places, okay, here, with rounding. All right, and in fact, if we go up to n equals 1,000 little trapezoids, oh my goodness, look at this. Our first 3 digits are right, and in fact, let's see, we're actually not that far off. In fact, I'm going to jump to the very last slide of this presentation, of this here, this one that's called summary. So for our 3 different sample sizes, n equals 100, 1,000, 10, 100, and 1,000. These are the values that we got by the endpoint rule, midpoint rule, and trapezoid rule, with the right answer being over here. A little hard to visualize the pattern there until I take, these are the errors that we got here. This is how far off we were from the right answer each time. And you can see for our endpoint rule that the errors are always bigger than they are at the midpoint rule, and the midpoint errors are always bigger than the trapezoid rule. And notice that the errors get, well, that's not quite, this one's actually a little bit smaller. Here, the midpoint rule did a little better than the trapezoid rule at 1,000, but in general, you can say that the trapezoid rule is going to generally work better. And notice that the bigger the sample size, the number of rectangles n or trapezoids gets, the smaller the error gets. All right, so those are the 3 trapezoid rule, midpoint rule, endpoint rule things. Now I wanted to show you one more thing. Here is our Monte Carlo method. Okay, so Monte Carlo method was another type of integration that we were going to do. Remember, this is the one where you're going to make it a game of chance, where you have invented a game where you are, in this case, trying to estimate the area under an integral by effectively throwing darts or whatever. You're going to circumscribe a rectangle around the integral, and then choose random points inside that rectangle and count how many of them are under or above the rectangle. Now, you won't be doing this on this homework set, but I just thought I'd show you. Okay, on this particular case, you can circumscribe a rectangle around that integral. Again, I had a graph of the equation to work with. The x would range on that rectangle from 0 to 10, which isn't really all that surprising when you look at the limits of the integration. And the y will be ranging from 0 to 13. 13 is the maximum value this equation can obtain. So if you had a rectangle that was 10 units wide and 13 units tall, the integral is completely inside of that region. So if I keep picking points inside of that rectangle that has an area of 10 times 13 equals 130, every point, when I choose a point in there, it'll either be above or below the curve. So what I used, again, you're not necessarily, going to be doing this on the homework, but I wanted to show you here. So like I picked a random value for each of 1,000 points that I'm going to drop here. I picked a value where x goes from 0 to 10 and y goes from 0 to 13. I just picked a random value using the rand function in Excel. Now for that location, for this value of x, I plotted a value, I said what is f of x. So I just computed, if that value is my value of x, this is what the value of f of x is this point under then? All right, so I have an if function in Excel. If the value is less than f of x, then put a 1 in here. Otherwise, put a 0 in here. For all 1,000 of these points that I dropped, then I just have a little n is equal to the sum of all those points. In this case, 509 of my 1,000 points were under the curve. All right, you plug in your equation for the estimates using the Monte Carlo method. It's little n over big N times A, and I got an estimate this time of 66.17, which is not a great estimate to the number of 70, but it's also not terrible considering we did the very simple thing here. I know I can force it to recalculate too. Here I drew a different set of 1,000 random numbers. All these numbers changed. All the values of f of x changed. All these changed. This time 544 of the values were under, the points I chose were under the curve. Again, if we forced it here to do the recalculation, now our value of our estimate is 70.17. In fact, if we did this again and again, here we estimated 71.89, 66.3, 66.7. None of these estimates are like spectacularly good, but n is equal to 1,000 is not really great for Monte Carlo methods. You want bigger numbers than that. So let's go ahead and look on the last tab here for a Monte Carlo simulation where n is equal to 10,000. Yes, if you actually scroll down here, I have 10,000 randomly chosen points inside of that region from x is equal to 0 to 10 and y is in the region from 1 to 13, 0 to 13. Again, for every value of x I picked, I computed the value of x and determined whether it was under or over the curve. That gives us a value in this case of little n is equal to, again, I just summed up all those if statements and got 5,355 points. Using our equation, little n over big N times a, we get 69.6. That's not a terrible approximation to 70. And in fact, we can force it to draw 10,000 new numbers here. Look, this time I got 71.16. This time I got 70.46. These are definitely closer. By using bigger values of n, I got a closer estimate to the real value of the integral. And honestly, n equals 10,000 is a very, very tiny sample for Monte Carlo methods. Typically, when a Monte Carlo simulation like this or a Monte Carlo method like this is used in numerical integration or something, you know, we might use 10 million or something. Now, an Excel spreadsheet is not the right tool for the job then. Then you would want some little C program or some little Python script or something where the math is being done not in some Excel spreadsheet, but in a little program. I mean, in a Monte Carlo integration program like this in a computer programming language like C would only be a few lines and would solve this to his, you know, I mean, a computer can draw 10 million random numbers in a fraction of a second and evaluate this integral as close as you want it. You need a closer estimate, make it at 20 million instead of 10 million. Okay, it'll take twice as long, but I mean, we're talking a fraction of a second. Computers can do these kinds of mathematical calculations very, very easily. All right. These are the methods that you're going to be using. In practice on homework 14, you're only using endpoint, midpoint, and trapezoid. We'll be learning more about numerical methods over the course of the semester, but and we're not going to get bogged down in how you come up with like error bounds as to like how good of estimates these are and so on. But suffice to say, those kinds of things exist. All right. If you have any questions, please let me know. This has been Dr. John Schrage.